Hello everyone, my name is Fasika Imam. I am a physics instructor at Kelebawi International Academy. My today's presentation is designed to grade 12 national exam candidates. And this revision is about vector physical quantities. So, let's start our discussion by definition of physical quantity. Physical quantity is one that can be measured and consists of a magnitude and unit. And these physical quantities can be categorized by magnitude and direction as scalars and vectors. So scalar quantities are quantities that have magnitude only. When you say magnitude only, it means that it's just a number value with units. The other type of physical quantities is vector. So vector quantities are quantities that have both magnitude and direction. For instance, as you can see from the screen, there is a force applied on the man which is 100 Newton in the left direction. So here there is a magnitude of 100 Newton in a direction towards left. And there are some examples of scalars and vectors. For instance, distance, speed, mass, time, pressure, energy, volume and density are examples of scalar physical quantities, whereas displacement, velocity, weight, acceleration, force and momentum are examples of vector physical quantities. We can represent vectors both graphically and analytically. So vectors are represented by drawing arrows graphically, and the length and direction of a vector should be drawn to a reasonable scale size and show its magnitude. For instance, if you see on the screen, 10 km is denoted by an arrow, and similarly 20 km is also denoted by an arrow. So the length of the arrow determines the magnitude. So as you compare here, there is a reasonable scale size between these two displacements. The other one is analytical representation of vector physical quantities. And vector quantities can be identified by bold type with an arrow above the symbol. Here there is one example, which is velocity. It says 23 meters per second north of east. So here V is bold, and we put an arrow over the head of the letter to show that it is a vector physical quantity. Let's look at graphical method of vector addition. So suppose we have two vectors A and B that are shown on the screen. Then to find the resultant of these two vectors, let's connect the head of vector A to the tail of vector B. In this case, the resultant vector will be a vector drawn from the tail of vector A to the head of vector B. And this method of vector addition is called triangle method or triangle law. If you have number of vectors, aligning vectors head to tail and then drawing the resultant from the tail of the first vector to the head of the last vector will give you the resultant vector. The second type of graphical method of vector addition is the parallelogram law. So the parallelogram law of vector addition states that if two vectors acting at a point are represented by the sides of a parallelogram drawn from that point, their resultant is represented by the diagonal which passes through that point of the parallelogram. As you can see on the screen, we have a parallelogram made by vector A and vector B. So the diagonal, which is the red arrow, is the resultant of these two vectors. And the magnitude of the resultant vector is given by the cosine law. So for these two vectors A and B connected tail to tail, to find the magnitude of the resultant vector, we can apply this law. And the law states that magnitude of the resultant vector equals the square root of A squared plus B squared plus twice of AB cos theta, where theta is the smaller angle between the two vectors, and its direction is determined by sine law. So you can see the sine law or the sine formula. So you can see the sine law on the screen, which says sine of alpha over B equals sine of beta over A equals sine of theta over R, where these angles are the angles that are found opposite to their corresponding side. Let's come to subtraction of vectors. Subtracting a vector B from vector A is adding vector A to the negative of vector B. So if we have opposite vectors, these vectors are directed in opposite way. So you can see on the screen that if you have vector D, which is equal to vector A minus vector B, you can rewrite as vector A plus negative of vector B. Now let's look at different types of vectors. The first one is equal vectors. Two vectors A and B are said to be equal if they have the same magnitude, direction, and if they represent the same physical quantity. As you can see on the screen, you have two vectors A and B, and these two vectors have magnitude of 5 meter and they are parallel, meaning they show the same direction, so that we can say that these two vectors A and B are equal vectors. The second type of vector is null vector or zero vector. So this zero vector is a vector having a magnitude of 0 and arbitrary direction. If you have two equal and opposite vectors representing the same physical quantity, then the resultant of these two vectors will give you a zero vector or null vector. The other type of vector is unit vector. So as the name indicates, unit vectors are vectors having magnitude of unity or 1, and they have a particular direction. To find the unit vector of a certain vector, let's say vector A, it's calculated by the given vector A divided by magnitude of vector A. And for three-dimensional rectangular coordinate system, we have a known unit vectors. These unit vectors are called unit vector I, unit vector J, and unit vector K, directed towards x-axis, y-axis, and z-axis respectively. Now let's come to resolution of a vector. Whenever you have a certain vector which is found in space, you can resolve this given vector to the known x, y, and z axis. You can resolve this vector to the known axis. For instance, if you look at the screen, we have vector A, which is drawn from the origin on the given space. So this vector A makes an angle of alpha with the x-axis, and angle beta with the y-axis, and angle gamma with the z-axis, meaning this vector has three different components. So we can represent the given vector in terms of its components, and we can rewrite this vector A analytically in such a way. So vector A equals ax in the I plus ay in the j plus az in the k, where ax, ay, and az are the x, the y, and z component of the given vector A. And if you want to know the magnitude of this vector, you can calculate it by the square root of ax squared plus ay squared plus az squared. You can also find the angle made by vector A with these three axes, and this cosine value of these angles is called direction cosines. And if you take, for instance, cosine of alpha, it is equal to the x component of vector A divided by magnitude of vector A. Similarly, cosine of beta equals ay divided by magnitude of vector A, and cosine of gamma equals az divided by magnitude of vector A. Now let's come to component method of vector addition. Suppose we have two vectors, vector A and vector B, that are described by their components as A equals ax in the I plus ay in the j plus az in the k, and vector B equals bx in the I plus by in the j plus bz in the k. Then to find the sum or the difference between these two vectors, you have to add or subtract component wise, so that A plus B, which is vector A plus vector B, equals ax plus bx in the I plus ay plus by in the j plus az plus bz in the k. The same is true for the difference between these two vectors. When you come to multiplication of vectors, we have two different types of multiplication of vectors or vector products that are called the dot product and the cross product. Let us see the first one, which is the dot product of two vectors. So the dot product of two non-zero vectors A and B is denoted by A dot B, and it is defined as magnitude of vector A times magnitude of vector B times cosine of theta, where theta is the smaller angle between the two vectors. So when we multiply two vector physical quantities using a dot, the final product will be a scalar physical quantity. And because of this, we sometimes call this dot product as scalar product. And there are some properties here as an example, like commutative property and distributive property over addition. And these two properties are valid for a dot product of two non-zero vectors. Now let us see the dot product of unit vectors. For instance, if you take vector A as unit vector I, for instance, if we denote vector A by unit vector I and vector B by a unit vector I again, then the dot product of these two vectors will be the magnitude of unit vector I times cosine of the angle between these two vectors. But here, since both vectors A and B are denoted by the same unit vector I, then the angle between these two vectors is 0 and cosine of 0 is 1. As you all know, the magnitude of any unit vector is 1 and hence the product of this will be 1. And therefore, we can generalize that I dot I, J dot J and K dot K equals 1. But if we multiply two vectors that are perpendicular to each other like I dot with J by using definition of dot product of two non-zero vectors, the dot product of I with J will be magnitude of vector I times magnitude of vector J times cosine of the angle between I and J. Here you have to bear in mind that the angle between I and J is the same as the angle between x-axis and y-axis, and which is 90 degree. And we know that cosine of 90 degree is 0. From this, we can conclude that I dot J, J dot K, K dot I equals 0 because the angle between these unit vectors is 90 degree, or they are orthogonal to each other. Now, let's assume that we have two non-zero vectors that are expressed by their components. Let's say vector A equals ax in the I plus ay in the j plus az in the k, and vector B equals bx in the I plus by in the j plus bz in the k. Then to find the dot product of these two vectors, you have to apply the concept that we already stated before. And finally, the scalar product of these two vectors will be ax bx plus ay by plus az bz. The other point here is projection of a vector. So when we say here projection of a vector, for instance, we have two vectors, vector A and vector B, as you can see on the screen. Then if we want to project vector B on vector A, first we have to draw a line like this dotted line as you can see on the screen, which is perpendicular to vector A. And then you have to draw a vector from this, the common point between the two vectors towards the dotted line which touches vector A. And as you can see on the screen, there is a blue arrow, and that is called the projection of vector B onto vector A. So in symbols, the vector projection of vector B onto vector A is given by A dot B divided by the square of the magnitude of vector A times the given vector A. But if you want to know the scalar projection of vector B onto vector A, it is simply the component of vector B that is in the direction of vector A. Meaning, the scalar projection of vector B onto A equals magnitude of vector B times cosine of theta, where theta is the smaller angle between the two vectors. The other type of multiplication of vector is cross product or vector product. Whenever we multiply two vectors using cross, then the product will be another vector, and that new vector is always perpendicular to both vectors A and B, or is perpendicular to the plane made by these two vectors A and B. The cross product of two non-zero vectors A and B is defined as magnitude of vector A times magnitude of vector B times sine of theta times unit vector n, where unit vector n is a vector perpendicular to the plane containing vector A and vector B. Now, if we assume vector A and vector B as I and j respectively, then the cross product of these two vectors I and j will be k, because vector k is a unit vector which is perpendicular to both vector I and j. So similarly, j cross k will give us I and k cross I will give us j. In this case, commutative property is not valid, and because of this, if you have j cross I, it will be minus k, and k cross j give you minus I, and I cross k will give you minus j. Now, if you have, for instance, the same unit vectors for vector A and vector B, for instance, I cross I, since these two vectors are in the same direction, the angle between them will be 0, and sine of 0 is 0. So, the cross product of two vectors that are parallel to each other will give us a zero vector or a null vector. And to find the cross product of two vectors that are expressed by their components, you have to apply matrix method, and then finally you will have this formula to find the cross product of two vectors A and B. So A cross B is equal to AYBZ minus AZBY in the I plus AZBX minus AXBZ in the J plus AXBY minus AYBX in the K. So there are some properties of cross products of two non-zero vectors. So commutative property is not valid or applicable for cross product of two vectors because A cross B is equal to negative of B cross A. But distributive property over addition is valid, and there are also other properties that you can see on the screen. So as I mentioned earlier, if the cross product of two non-zero vectors give you a zero vector, then you can say that these two vectors are parallel to each other. Now let's look at some examples of this lesson. So let's recap all the points that we have seen so far by doing some examples. So let's look at some examples as a revision for our today's lesson. The first example says find a unit vector that point the same direction as vector A, where vector A is minus 5 in the I plus 2 in the J plus K. So to find a solution, first let's determine the magnitude of vector A. As I mentioned earlier, to find the magnitude of vector A, it is calculated by the square root of AX squared plus AY squared plus AZ squared, where AX is minus 5, AY is 2, and AZ is 1. These values in the given formula, and finally you will have rule 30 for magnitude of vector A. Now to calculate the unit vector A, you have to divide the given vector A by its magnitude, so that the magnitude of this unit vector A will be minus 5 in the I plus 2 in the J plus K divided by root 30. The second example says if vector A equals 3 in the I minus 9 in the J plus K and vector B equals minus I plus 8K, find the resultant or the sum of these two vectors. To calculate the sum of these two vectors A and B, we have to apply component method of vector addition, so that A plus B, which is vector A plus vector B, equals AX plus BX in the I plus AY plus BY in the J plus AZ plus BZ in the K. So these X, Y, and Z components should be selected first and substitute on their corresponding variable. And hence A plus B equals 3 plus minus 1 in the I plus minus 9 plus 0 in the J plus 1 plus 8 in the K. And finally, the resultant of these two vectors A and B equals 2 in the I minus 9 in the J plus 9 in the K. Let's look at the third example. Given two vectors P and Q, where P is 2 in the I minus J plus K and Q equals I minus 3J plus 2K. And we are asked here to find the dot product of these two vectors P and Q. To give a solution here, since both vectors P and Q are given in terms of their components, to calculate the dot product of these two vectors P and Q, we have to use the equation which says Pxqx plus Pyqy plus Pzqz. Now let's plug out their components first and substitute on the given formula. And it will be 2 times 1 plus minus 1 times minus 3 plus 1 times 2. And finally, the dot product of these two vectors P and Q equals 7. Our final example for today is this one, and it says that if vector A equals 2 in the I plus J minus K and vector B equals minus 3 in the I plus 4 in the J plus K, then calculate A cross B. So to calculate the cross product of these two vectors A and B, we have to apply matrix method, and then finally we will have a result which says A cross B equals 5 in the I plus J plus 11K. Here, if you already know the formula, the final formula of the cross product of two vectors A and B, you can also directly substitute their component values from the given and find the same result like this. In today's lesson, we have seen some major points about definition of vectors, types of vectors, addition and subtraction of vectors, and multiplication of vectors. I hope you enjoyed our today's lesson, and that's all for today. Thank you.